Are we? Oh yeah, you're in.
This one?
I've never seen you in there. Sorry.
Alex, I'm back here. I know, just go talk, sit. Not talk. Go for a minute. Come on. There you go. Watch your step, but that way you're distracting us. Okay.
I can hear Alex perfectly from my locker.
What?
I can hear you perfectly from my locker.
So you're pointing out the problem. Alright, so my name's 875, close to 50. Guys, why am I taking the time to do this when really it's just a plug and chug? What did I tell you is tricky when it comes to bearing?
The negatives.
Nope. Yes, okay, I already said that. Yes. The angle. The angle and what it means and what it shows. Okay? So I'm throwing in my calculator really fast just so we can get it. Someone back me up, please, if you don't mind. 50.5507-ish. Look good?
Yep.
I just have to change. I can copy and paste. Man, I'm saving time on my calculator. You guys know how to copy and paste, right? If you don't, that's helpful. Not on the calculator, though. And then negative 129.2065. Does this make sense with my picture since I made the signs that I understand?
Yes.
Is it going positive and is it going down?
Sure. Yes. Yeah. No. Oh.
Isn't the wind pushing positive and up?
Oh, yeah.
So what did I do wrong? I forgot to put my little negatives in my little numbers. So I did not have the right answer. It should be minus a negative, which is a plus. There we go. It should be a positive 121. Now does this make sense with the wind? Is it pushing right and up?
Yes.
It's pushing right and up. The wind is, if I'm looking at it now. If I throw that into Pythagorean theorem, it's going to be no big deal. I can do the square root of that nasty 50 dude squared plus that nasty 129 dude squared. And I just do the square root. I plug it in one little line in my calculator and I get 138.743. I guess we just do 1.
0.16.
Kilometers per hour. But when it comes to tangent, inverse, I still use my formula. It's not wrong. I still go use my B, which is the 129-ish guy, over my A, which is the 50-ish guy. This would be wrong. No, the math isn't wrong. This just isn't the answer in the back of the book.
Yeah.
Okay, but wait, why? Didn't I change how I was measuring angles?
You gotta change it back.
I changed how I was measuring angles, right? Wasn't I measuring angles like first quadrant angles and putting signs on it? So hold on. If I tangent inverse of B over A, what I'm doing is I'm taking this little wind guy, I'm blowing him up, and I'm saying, okay, little wind dude, I got you. Your little opposite is 129 point blah blah blah. Your adjacent is 50 point blah blah blah. I'm finding this one. Tangent inverse of opposite over adjacent. I'm finding this one because that's the one we always find. But wait, how are these angles being measured?
You gotta add 90 to it.
Not add 90. Careful. It's not in the fourth quadrant, so it wasn't that 90 was taken away, Alex. I'm measuring it in the first quadrant. When bearing says, no, you start from north. You start from north. Bearing is weird. Bearing is different. You're not starting from due east, you're starting from due north. I don't want this guy. I want that guy. I want it to be in context of the rest of the picture. In context of, oh, this life lesson's there. Consider your surroundings and then try to anyway. Yeah. I need to do 90 minus. I need to do 90 minus. That's why I took the time to go ahead and plug it in and get the decimals. Because you don't want the 68-ish. You want the 90 minus for your bearing. Because it wants direction. But not the direction that we're using. Not with the same old words or the same old angles that we always use. They need it put into a different context in order to understand it. Oh my goodness. There's life lessons with evangelism right there. Anyway, 90 minus the 68-ish. Sophia, are you checking? It's not bearing at, sorry, it's bearing of, is it 21.38 or no, 37? 1.4 dot products. You guys have this all written down? We have this formula of a dot product. Let's go ahead and see if we can figure out how to use it. Because using it is not all that bad. Applying it can get tricky. Kind of. But not as general and broad as the vector ones that you just saw where it's like there's this, there's that. For this section, it's very specific to be like, you can use it for finding orthogonal vectors. What? Anyway, don't worry. You can use it for this, you can use it for this, and then that's all we're going to show you. So it's very specific. It's not quite as like, who knows what's coming. This one, I'm going to get these components up with vector W. It'll make life make a lot more sense. But do you guys realize that these examples, they're even reminding you that vectors can show up different ways. They don't always show up with components, right? Can't they also show up in linear combinations like the i's and j's up above? Oh, come on, computer, please. All right, guys, while I try and manage to get the little busy signals. If you don't like the linear combination, what can you always do?
Blow it up.
Well, not blow it up, but you can rewrite it. Make it components. So what would they be in components? Yeah, if you don't like it, rewrite it. You can't always do that in life, sometimes you just gotta deal with it. But if you don't like the linear combination, rewrite it. Because in the components, it's kind of how I have the formula over there. Because check it, if I was to color code for some of you, that makes things a lot easier.
Why is the screen so weak?
That's a great question for God and the computer and the people that take care of our computers.
Bruh.
They do what they can. But if you guys look over there, if I was to color code, if I was to be able to do things right now, wouldn't U1 times V1 come from the first two numbers in the linear or in the component forms? And then wouldn't U2 and V2 come from the second two numbers? So check it. I want you guys to go ahead and, since you can, right? I can't. Can you put U dot V? Because that's what we're trying to find. We're trying to find the dot product. U dot V equals. And then no components, no i's and j's. The dot product is a single number. Please. It's a single number where you take the x times the x plus the y times the y. It's as easy as that. The x times the x plus the y times the y. So, Alec, you're filling it in. What are you writing? You're writing 4 times. 4 times negative 2. No, the x times the x. What's the other x?
Wait, it's 4. Oh, I'm doing the wrong one, sorry. I'm doing number 11.
Yeah, that's what I want. What's the other x?
4 times 2, right?
Nope.
Wait, it's 4 times 1.
There
So negative 2 times
There we go. That's what I was looking for. Because this guy became 4, negative 2. So the x times the x would be 4 times u dot v. Ooh, do you have your vector arrows? Is 4 times 1 plus negative 2 times negative 1, which is? Wait, it's a number? Yeah, it's a number. It's a helpful number. It's a useful number. It's a very commonly in physics used number. But it's a number, not a vector. So what happens when you multiply a vector? It's a number. So what's down here? If we have to do v dot u. Oh, wait a minute. V dot u. Can you do x times x plus y times y? What's the x times x of v dot u? X times x. Negative 4 times 3 plus y times y. Since this is a commonly used formula, we're just getting the hang of it and how to plug in. And then w dot v, okay, x times x, right? Plus y times y. Now do you have some pen pals? Yeah, I have some multiplying I need to do before I can do my parentheses. And I have some other multiplying to do before my parentheses. But then if I can do my parentheses, hopefully I'll be able to eventually get to my final number. Dot products. They're not like doubling a vector or adding or subtracting a vector that gets a net result. Multiplying vectors gets us a very special constant that can be used and is used in many different relationships in physics. And so even though we're not finishing this today, which is why homework can't be due tomorrow, which is okay, I kind of already knew that, which is why I budgeted a test, which was supposed to be on Monday, which no one wanted anyway. Because we only have sections 6.1 to 6.5 in this chapter, we're getting close. And 6.5, we're probably going to shortcut. It's one of those for the future that we might not necessarily need as much. The test is now on Tuesday, just for you guys to be thinking forward, which also gives us 2 non-chapel days to be working. And lets us avoid a test on a Monday, which is a good thing. You're going to see, though, on this next page, even though we're not going to get to it entirely, that it's not so much that for pre-calculus you have to memorize this random formula. It's more of giving you a chance to practice things that you've learned in the context of one application where it's going to be used out there in physics. If you want to find the angle between two vectors without having to shift and use geometry of parallel lines and supplementary same side interior angles, you can actually find it once you know the dot product. And as long as you know that these are magnitudes, and as long as you understand to find an angle inside a cosine, use a cosine inverse. So many things you wouldn't have had any clue how to even plug in if you hadn't taken this course. Now, maybe in college someday, if you're in a physics course, they would have quickly shown it to you and been like, well, you should have learned this before. Go look it up. But now you're in this class, you're like, that's magnitude. That's the square root of a squared plus b squared for him. And for him, that's the dot product. Multiply the x's plus multiply the y's. The angle's inside a cosine. No stress, cosine inverse will undo cosine. So we're just learning how to work with a few formulas that you might see one day, because in physics there are tons of formulas. So the more you can understand the pieces, the more you'll be able to use. Does that kind of make sense? Okay, but this isn't the only formula. We're going to see a few different ones with dot products, and we're going to practice with them. You guys are feel better.